hopefully you already finished the lab from the other day, total internal reflection. This is going to be section 17.2, and we're going to be taking a look and reviewing those details and covering all those aspects and calculating what that critical angle is going to be. So I'm using a ruler. You don't have to. If you don't want to, you can sketch this out if you like. But this is going to be the surface of the water, and this is going to be the air. So here we have the air, which is up here, and then we're going to have down below, we're going to be having our water as well. So to remind you, air is less dense than water. So this is denser, not only in terms of physical density, but optical density as well. Air is 1.0, water is 1.33. So air is 1.00 for the index of refraction, and the index of refraction for the water will be 1.33. And we're going to be starting out taking a look at a couple of rays of light. Let's go ahead and draw our normal. Remember, your normal is perpendicular to the surface in which the light is coming in. And we're going to be taking a look at our first incoming angle of light. So this is going to be the incident beam of number 1 coming in. This is going to be forming the angle of incidence. Now remember, we're going from water going to less dense. If we're going to denser, it bends toward the normal, but we're actually going to be bending away from the normal because we're going into something that is less dense. So I'm going to be drawing this out like this, and this is going to be the refracted angle coming from light 1. And again, we measure from the normal to the ray, and it's the same thing here. We measure from the normal to the ray. So this is going to be the refracted angle coming from 1. So if we have a larger angle coming in, okay, let's say we have this angle, we have incident ray number 2. And it's going to be bending away from the normal. Again, it's going to be bending like this. And so this angle right here would be our angle of incidence number 2. And this would then be the refracted angle coming from number 2. Okay, so the question is, what is the angle going to be that produces this 90-degree refraction? So what's this angle? Here's the question mark. What angle does this have to be in order to produce a 90-degree refraction? This is called the critical angle. So the critical angle is therefore going to be the angle of incidence, this whole angle right here. This would be the angle of incidence number 3. The angle of incidence that produces a 90-degree refraction. And again, that 90 degrees is measured from the normal to the outgoing refracted ray of light. And as we discussed in the previous lab, if we have something that's greater than the angle of or the critical angle, so this would be I4, what happens is we get total internal reflection. So this would be the reflected angle. And I'm going to do lowercase reflected 4 because this is no longer refracted, it is reflected. So the angle right here for theta I4 would be equal to this angle right here, which would be theta lowercase r4. So again, this is the definition of reflection. The outgoing angle is going to be equal to the incoming angle. It's going to be equal to the angle of incidence of the light that's coming in. And again, we're measuring it according to the normal down below here. So let's go ahead and calculate. And also this is producing total internal reflection. It's just an acronym that I've created for myself and for us, so we don't have to write that down a lot of times. So here, the angle is smaller than the critical angle. It's going to get refracted. Smaller, it gets refracted. The critical angle also gets refracted at 90 degrees, but anything larger than that critical angle is going to be reflected. So let's take a look, and we're going to calculate what is the angle that is going to produce a 90-degree refraction. So we're going to go back to Snell's law, and the index of refraction for the incoming material times the sine of the incident angle will be equal to index of refraction of a refracted material times the sine of the refracted angle. So we're going to be coming from the water. That's our incident ray of light coming in. So we're looking at I3 right here. What's this angle? That's what we're trying to calculate. That produces a 90-degree refraction. So this is going to be in the air. So this is going to be 1.33. This is what we're trying to solve. This is going to be my air, which is 1.0, and this is going to be my 90 degrees. So we're going to be plugging in the 90 degrees into this in order to calculate what the incident angle is going to be, which is going to be the critical angle. So let's go ahead and rearrange. We're going to divide both sides by the index of refraction of water. So we have the sine of the incident angle, which is the critical angle, equals the index of refraction for air. That's 1.00, if you remember. So this is going to be the refracted, and this is going to be my incident. So that's going to be 1.0, that's going to cancel. Is going to be equal to the sine of 90 degrees divided by the index of refraction of the incoming, which is the water, 1.33. Well, if you go on your calculators, you'll see that the sine of 90, that's going to be equal to 1. So that's going to all cancel out, and it's going to be 1 over 1.33 divided by 1.33 equals, and now what we need to do is do the inverse sine of both sides. So if we take the inverse sine of this, this tells us that it's going to be 48.75 or 48.8. So the critical angle is 48.8 degrees. Truly 48.75, because if it was 48.8, we'd actually be slightly beyond that critical angle. So again, let's take a look at what happens if I have an angle such as this right here, which is beyond my 48.8, such as we did in the lab. If that's the case, let's go ahead and we're going to take just even at 49 degrees. So I'm going to rewrite Snell's law. Okay, again, we're coming from water. We're going into air. And we're going to be plugging in 49 degrees into our angle there, which we already know is going to be beyond the 48.8. We're going to try to solve for what will the refracted angle be. So we're going to divide both sides by the index of refraction of air. But again, the index of refraction of air is 1.0. Those cancel each other out, and that's going to be all above 1. So we're going to have the index of refraction of water, 1.33, times the sine of 49 degrees is equal to the sine of the refracted angle. Once again, I'm going to be taking the inverse sine of both sides. So we'll take 1.33 times the sine of 49, and then when we do the inverse sine of that, we get error. So again, if we get error on your calculator, that means it's not refracted, but it's actually going to be total internal reflection. So that's total internal reflection, and here's a couple places where we see total internal reflection. And one of the places that we see them are in these fibers, or in fiber optics. Light is able to travel down these fibers, and they come out the ends. This is how some signals are sent. It's kind of the old school method before satellites and other technologies, but information can be sent through these fibers, and that's how international calls were made, and your phone signal was sent through these fiber optic cables all the way across the world, really, and that signal would be transmitted in the form of light like this. And on the other end, those it's sort of like Morse code, but with light. Those codes would then be received on the other side and then transcribed into the voice that's coming along with it. So here is a fiber, a long fiber we can take a look at here. And we're going to be taking a look at, let's say we have an incoming ray of material or of light, and it's coming in like this, and here is the normal. Well, if we are not at the critical angle, what's going to happen is this signal is going to leave the wire because it's going to be refracted, and again, it will be refracted away from the normal because this is going from the fiber and it's going into the air, so it's going to something that's less dense. Denser things, again, bend toward the normal, going into less dense, bend away from the normal. So this would be our angle of refraction right here. However, if the beam of light is coming in and that beam of light is going to be larger than the critical angle, what happens is we will then have total internal reflection. And if you remember from geometry, if we have reflection, this is going to reflect as well because it's going to be the same angle coming in and the same angle going out. If you remember your parallel lines and your alternate interior angles, etc. Okay? So what's going to happen is that this will be total internal reflection, and that will continue on forever. So these are often used, this principle is used in fiber optic cables which send messages. Last thing I want to talk about is how total internal reflection is seen in rainbows. So imagine you have a rainstorm. You need a couple things for a rainbow. You need to have raindrops, of course, and you need sunlight. So let's go ahead and draw a raindrop. So here's the raindrop. And imagine that the sunlight is coming into this raindrop. Okay, so the sun. The sun is composed up of white light. What's going to happen is that this white light, this drop is going to act as a prism. When the light hits that drop at a particular angle, it's going to then separate this one white light into all the colors of the rainbow. And so all the colors of the rainbow from Roy G. Biv. So let's say this is going to be our red up here, and we're not going to draw all the colors, but this is going to be our violet down below here. When the sun comes in at a particular angle, the drop acts as a prism, and what happens is both of these rays are going to have total internal reflection. So we have total internal reflection on the inside of the raindrop, again, when the sunlight's coming in at a particular angle. What happens is the red light is going to then reflect like this. The violet light is then going to reflect like that. And the violet light will then refract back out into the air like this. And the red light is going to be reflecting down like this. Now imagine that you are an observer and you see the sun and you see this rainstorm and you're looking up. Here's your eyeball looking up. What's going to happen is this one beam of light is going to come to you, and it's going to come to you as red. So let's go through this process again with a second raindrop. Imagine here's this raindrop over here. Okay, the sunlight's going to be coming down as it did before. It's white light coming in. It's then going to act as a prism. So the red light will go here, and the violet light will go here. Red to violet. What's going to happen is the red light will have total internal reflection, and that beam of red light is going to go somewhere else. What's going to happen is the violet is going to have total internal reflection, and then that's going to come to your eye as violet light. So this is just one raindrop producing one single beam of light to your eye as red. Well, what's missing in between is we need another raindrop for orange, we need another raindrop for yellow, we need another raindrop for green, blue, another one for indigo as well. But it's not just having red, orange, yellow, green, blue, indigo. It's not just having 7 raindrops to produce the rainbow. You need trillions of raindrops because this is producing one beam of light, pure red. This is producing pure orange. This is producing pure yellow. Well, we need all of those that are in between orange and yellow, all of those that are in between yellow and orange, all those in between green and yellow, all those drops that are in between these, all the drops that are in between here, et cetera, et cetera, et cetera. So we need trillions of drops. Trillions of drops, okay, that are needed to produce the continuous spectrum. So trillions of drops to produce the continuous spectrum a visible light that contains all the colors of the rainbow. Trillions of drops to produce continuous spectrum, which is going to be all the colors of the rainbow. And that's how we see a rainbow. So each droplet acts as a prism, and you have total internal reflection on the inside of the drops, which then reflects and then refracts one particular wavelength of light to your eye. Collectively, all those drops will add together, and that will create the rainbow.